we are going to talk about normal distribution. This is a very important topic in statistical analysis and doing inference on a data set that is available in real life. We often use this normal distribution to characterize our data sets, and the data can be generated from various places, like there can be economical data, that the data can be collected from share market, the data can be collected from various other places, etc. So the normal distribution is a very important part in modeling the statistical distributions in real life. So today we are going to talk about normal distribution. So let's go to the next slide. So the main phenomena of normal distribution is that it's a bell-shaped curve. As you can see, it's a bell-shaped curve, and the tails are not the tails of this normal distribution, that is the two end parts of the normal distribution, do not contain very huge amount of probability. The most of the probability is concentrated at the center. So this curve, as you can see, is uh, is the density curve of the normal distribution. It looks like a bell, so that's why it's a bell-shaped distribution. Uh, and this distribution is symmetric about the center of the distribution, that is the mean of the distribution. So this now we'll talk about why is this distribution so important. So let's come to the definition. What do we mean by normal distribution? So this is a continuous frequency distribution of infinite range. Now, continuous means that, as you can see, that the density curve of the normal distribution is continuous over the entire real line, and this distribution has a support of the entire real line. From the previous picture, as you can see, that this curve dies down on the both ends, and it's an asymptote towards the x-axis. So this distribution has a support from minus infinity to plus infinity, and it is symmetric about the mean of the distribution. So this is how it looks like when the mean of the normal distribution is mu and the standard deviation of the normal distribution is sigma. So that's what I mean when I say that the distribution has a support on the entire real line. That means the distribution is defined, that is the density function is defined on the entire real line. And this distribution is continuous, there is no jump, so this distribution is continuous, and since it is support has the entire real line, so it has infinite range. Now let's come to some important properties of the normal distribution. So normal curves are symmetric, single peaked, and bell shaped. That we can see from the picture. This is symmetric about the mean. This is single peak, that is there is only one peak at the center, that is at the mean of the normal distribution, which we call it mu, and their tails fall quickly, so that when we try to fit a normal distribution on a data set, we generally assume, if we can see that the data set doesn't have that much outliers, and that is the outliers are very unlikely to come, that's why we try to fit a normal distribution on the data set. So their tails fall quickly, so there is not much probability there. So that implies that the probability that there will be a very high value that is coming, that is the value is very far from the mean, that is very unlikely, because that's a very low probability event. So again, let's go back and see. So this, you can see that at the end there is only 2.5% probability after mu plus 2 sigma. So if a outlier has a very large value as compared to mu, then it is very unlikely to come in the normal distribution. So if we say that is mainly concentrated around a particular point, we try to fit a normal distribution on that data set, because that will approximate the data set in a more in a better way. So because normal distributions are symmetric, the mean and median are both at the peak. This is due to the symmetricity. This is a very important property of the normal distribution, and this helps us to do a lot of calculations in a very easy way. And this is easy to handle while we do the calculations. Now, use of normal distribution. As I have already said it earlier, that the normal distribution is a descriptive model that describes the real world situations. Like, for example, a typical example will be the height data. So suppose if I collect if I have a population of say 1,000 people, and I collect the heights of all the people, it is likely that there will be a peak at the average, and we take the average of all these heights, then there will be a peak at the average, and then it will, and a person with a very extremely high uh, height will be less likely to come. So for example, the height data has, we can fit a normal distribution, and if we collect the data, then we can fit an histogram on that data set, and from that histogram we can really see that it is indeed the case. So the next point I'm going to make is that normal distributions are often used in natural and social sciences. So this is just one or two examples of the data sets where we use normal distribution. There is lots of other places, lots of other different types of data that come that we can fit that data set with a normal distribution. So these are so this is the normal distribution, the use of normal distribution in various types of data. So these data are very much real life data sets, and that's why we need to learn about the normal distribution. That's the motivation of learning about normal distribution. Now, there might be many dependent variables that are commonly assumed to be normal distributed in a population. As I have already stated, the height data, maybe the weight of a population of people, that might also have a normal distribution. If a variable is approximately normal distributed, we can make inference about the values of that variable, like what is the probability that that random variable will take these values in a particular range. We can calculate it from this from the study of normal distribution. I will actually describe that how exactly we'll calculate the probability from a normal distribution of if we assume a random variable follows a normal distribution, but that will be at the end part of the lecture. So this is the importance of normal distribution. Now, as I have already stated earlier, that this distribution is symmetric. That's a very nice property of normal distribution, and that's why the mean, median, and mode is all at the same point. It's at the center, and you can see the green line here. The green line is indicates the mean on the x-axis, and the normal distribution is symmetric about the mean. There will be exactly 50% probability on the left hand side, and there will be exactly 50% probability on the right hand side of the density curve, like under the area of the density curve. And that's why intuitively we can see that the mean, median, mode is similar, and it is indeed the case mathematically too. So now expressing the normal distribution. So since we till now we have talked about normal distribution and everything, but when we are trying to do some calculations or we need to express it, so I'll try to explain the normal distribution, that is by some simple mathematical parameters. So normal distribution can be expressed in terms of only two parameters. One parameter is the mean. It is very from the previous picture also you can see that the mean is really necessary. If I shift the mean from left to right, then the peak of the density curve will also shift from left to right. But there is another important parameter of the normal distribution, that is the variance. If I fix the mean and variance of the normal distribution, then this curve will be a fixed curve. Reduce the variance of the normal distribution, then the peak of the curve will go up and there will be more concentration around the mean. But if the variance of this curve is large, that means there will be the peak will be shorter in height, and there will be more area towards the tail of the normal distribution. But still, and on the both sides of the mean, there will be the same probability, the 50% 50% probability of the normal distribution. So that's two important parameters of normal distribution. So it is very natural to express the normal distribution using these two parameters. One is the mean and another is the variance. So the variance controls the spread of the distribution curve, and mean controls the center of the distribution curve, where it is located. So often we call it mean as the location parameter, and variance is the spread parameter of the normal distribution. So now we are talking about probability density function, probability distribution function. Just a little bit of mathematical definition of probability distribution function. Probably you guys already know about the probability distribution function, but just a little recap. So every cumulative distribution function fx, x is the random variable, and we are trying to say something about the distribution function of x. This is a non-decreasing and corollary function. Corollary means that it is a continuous on the right and the left limit exists. So this is a corollary function. So this is a completely mathematical property, that how do we define the probability distribution function. And the second property, which is really necessary for a function to be a distribution function, is that if I tend x to plus infinity, then fx will take the value 1, and if x goes to minus infinity, it will take the value 0. So it is a function between 0 and 1. There can be some little jumps on the function, that is, there will can be little discontinuity in case of probability distribution functions. But the good thing about normal distribution is that it is continuous, so the probability distribution function will also be will be a continuous function. There will be no jumps, and that's why it is very helpful to deal with normal distribution, which makes normal distribution very easier to handle. Now, probability density function. So easiest and non-technical way of defining a function that is a function to be a probability density function is to say that it is the derivative of the distribution function, but provided there will be some mathematical conditions, like if the derivative exists and everything is nice, the limit exists, all these things. But these are mathematical details, we don't need to go about need to learn that. So that's the basic idea of probability density function. So when I say that the bell-shaped curve of the normal bell-shaped curve is the normal distribution, that means that the probability density function of normal distribution is bell-shaped. So that's why the normal distribution function is the probability density function is also is bell-shaped. So that's helpful in studying real life data sets. So there are some notations we use to express normal distributions. For example, so this is the general notation, that is normal mu sigma square. This is the notation that we use to describe the normal distribution function, to express that in normal random variable. And there are two parameters. One I have already told you about it, that the mean parameter is mu, and the standard deviation parameter is sigma, or the variance parameter is sigma square. Next, we use small phi for expressing the standard normal distribution function, and for expressing the standard normal density function we use capital phi. So so now what is a standard normal distribution? I'll come to that later. So I have already stated that normal distribution has two main parameters. One is the mean parameter, one is the standard deviation parameter. One is the standard deviation parameters. And for standard normal, if we fix the mean at 0 and the standard deviation at 1, then we call that normal distribution a standard normal distribution. We fix the values at 0. That is, if the normal distribution is centered at 0 on the x-axis and the spread is 1, then we call this normal distribution a standard normal distribution. So this curve, as I have already stated earlier, that this curve is asymptotic to the x-axis. You can see that the curve dies down on both sides of the both sides, since it is symmetric about the mu, but it never touches the x-axis. It goes on, and this is an asymptote on the x-axis. And the total area under the curve on the x-axis is 1 or 100%. So that's why it's a density function. We need to make to make a function a density function, we need to ensure that the total area under that density curve will be 1. So otherwise I cannot say that it is a probability density function. So since we are dealing with probability density function, so this is an obvious property of it. Now there is an empirical rule about the normal distribution. So the center line, that is the center of the red area, that's the mean of the normal distribution mu, and the where the red ends, that's the place where is the mu plus sigma, that is mean plus standard deviation, and the left hand side of this curve is mu minus standard deviation, that is yes, so mu minus sigma. So from mu minus sigma to mu plus sigma, under this normal probability density curve, there is 68% area of the data. This is the empirical rule, and that sometimes helps us very much to do some simple calculations in a very fast and easy way. So that's why we need to learn this. That let's write it down. So suppose this is our normal distribution, this is our normal density curve, and if we do like this, then this is on the x-axis mu plus sigma, and this will be mu minus sigma, and under this area will have 68% of the probability of the total is 100% of the probability, but this area will contain only 68% of the probability. So, and if we go to mu plus 2 sigma and mu minus 2 sigma, then this whole area, so this whole area will have then so this whole area, like here in the green area plus the red area, so this will have 95% of the data. And if we go to 3 sigma, then the blue, green and the red area will combine give us 99.7% of the probability. So we have 99.7% probability, and so both the tails, the remaining parts, will have only 0.3% of the probability. That's very small. So when I said that the normal distribution, it's very unlikely to get an outlier because it has a very less probability. You can see that from the empirical tool that the probability is 0.03%. The probability is 0.03. So so it's very unlikely to get an outlier in case of a normal distribution if we generate data set from this distribution. So that was the empirical rule of the normal distribution. Now let's see that how does this density function actually look like in a proper mathematical form. So the mathematical formula for the density curve of the normal distribution is, as you can see, fx equal to 1 by sigma times square root of 2 pi, then e power minus half x minus mu by sigma whole square. So this mu, this is the mean, as I have said earlier, this is the center of the normal distribution. And since we have this x minus mu by sigma whole square, so that's why that really indicates that it's symmetric. That is, whether x minus mu is positive or negative, it will have the same value. So that's why this function is symmetric about the mu. And sigma really contains the variance or the spread of the normal distribution. So this curve is the curve we are studying, and this curve is the bell-shaped curve with different centers and spreads depending on mu and sigma. And so this is the mathematical formula for the normal density function. Now the standard normal distribution is z. So we denote the standard normal as a random variable z. That's a notation for us. And if the mean is 0 and the standard deviation is 1, if that happens, then we call this normal distribution a standard normal distribution. So suppose we have a data set and we want to fit a normal distribution on that data set, but the mean is not 0 and the variance is not 1. So then if we assume that suppose a random variable x that follows that normal distribution, then we can change that x random variable by x minus mu by sigma, and then we denote it by z. Then this z will have a normal 0 1, that is a standard normal distribution. So that will be very helpful in the subsequent calculations. So that's how we that's why in the standard normal distribution is also very important. This is a special case of normal distribution. Now probabilities are depicted by areas under the curve in this case. So the total area under the curve is 1 or 100%, and the area in red is equal to probability z greater than equal to 1. So this is a standard normal curve, and so the area in red in this case is probability z equal to 1, and the area in blue is equal to probability between -1 to 0. So the, that's that's just an illustration of what I was just saying earlier. It's a simple illustration with colors. So introducing the height data. So I have collected a height data of 25,000 children of 18 years. So this data set is available in the hyperlink that I have presented in this case. So you can see that if you go here, so this is the associated. Okay, so yes, so this is the data set. So this is the data set. I used R to load the data set and then try to fit a normal curve on that data set. So this is the original data set that contains heights and weight of 25,000 children of 18 years. And so this is the histogram I have plotted in R using ggplot. So the so this is the So you can see that the height varies around from 75 to 175, and the red curve is the empirical curve. In ggplot, there is a function which we can use to plot an empirical curve on a histogram, and the blue line is actually the as the normal distribution, the best normal distribution that we can fit on this data set. So intuitively, the best normal distribution that can express this data set will have mu to be the average of all these data points, and has standard deviation as the standard deviation of the sample standard deviation of the data set. So that's what I have used, and then plotted a normal distribution on this curve, and you can see that the empirical curve, which is the red line, the red curve, and the normal curve, that is the blue curve, they're very close to each other and over the range. So we can say that our fit is reasonably good in this case. So this is what I was saying when I said that we sometimes fit a normal distribution to a real life data set. So that's what I was trying to say, that can be explained from this picture. So now say we have a statistical software that is called R, and we can use R to calculate various probabilities of normal distribution. So the density distribution function for the normal distribution with mean equal to mean and standard deviation equal to SD. So we can use two functions in R for calculating this. So D norm is the density function, and P norm is for calculating the distribution. So these are the two functions that's available in R. We can use these two functions to calculate the probabilities that we require. Now that's more or less all about normal distribution. Now let's try to find out how do we exactly calculate the areas under the normal curve. So let's try to find the area to the right of z equal to 1.25 and z equal to say minus 0.34. So the solution is in R code. If we write in the RStudio console that 1 minus p norm 1.25, and that's this probability, 0.10, around 0.11. So why did I do 1 minus p norm? So p norm, as I have said, is the density, is the distribution function, and so p norm, so p norm 1.25 means minus infinity the probability, and from minus infinity to 1.25, and when I do 1 minus of that, I'll get the probability after the on the right hand side of 1.25. So that's what I did. And similarly, the same way I can do it as p norm 1 minus p norm minus negative 0.34, and that's this probability. So you can see that the probability is greater than 0.5, the probability is greater than 0.5, which is obvious because we are dealing with a standard normal distribution, and so since this is a negative point, so it will have 0.5 plus some area from minus 0.34 to 0. So if we add 0.5 plus these two area, we'll get something like 0.63. So that's why it's intuitively true that it's intuitively we can guess it that it will be bigger than 0.5, and which is indeed the case. So the mean and the standard value are 0 and 1 in default, so we do not need to specify them here. So the in case of standard normal distribution, the mean and standard deviation are 0 and 1 respectively, so here we don't need to specify that. Now we deal with another example. So let's find the area between z equal to negative 0.24 and z equal to 1.23, and say the second problem is that we calculate the area from 0.15 to 2.04. Now how do we calculate this thing? So the solution is simple. In R, we write that p norm 1.23 minus p norm negative 0.24. So p norm 1.23 will calculate the area from minus infinity to 1.23, and p norm negative 0.24 will do the same, minus infinity to negative 0.24. If I subtract from each other, then I'll get the probability in between. So that's 0.48. Similarly, we do the same thing here, and the probability is 0.42. So this is how we write the code in R for calculating the probabilities. But there is also another option. If there is a normal distribution table also, there, from that table we also can calculate the probabilities in for this kind of situations. But now it's easier to do it in R. So there is applications of normal distribution. That's another problem, another sample problem, as just example problem. So this is an university that conducts placement of examination in all incoming freshmen. The examination scores of 1,000 examinees last September were approximately normally distributed. The mean score was at 80 and the standard deviation was 5. So now suppose we want to calculate what is the probability that a randomly chosen student will get a score below 70, or get a score above 82, or get a score between 0.75 and 90. So suppose we want to calculate these three probabilities. So how do we do that? So suppose we want to calculate first that below 70. So from the question we can see that the assumption that this follows a normal distribution has already been made, and mu equal to 80 here, sigma equal to 5, and x is less than 70. So we first calculate the z-score. So z-score is x minus mu by sigma, that is 70 minus 80 by 5, and z equal to minus 2. And so from the z-score we can use the normal table to calculate the probabilities. But in case of R, we do not need to actually calculate the z-scores. We can put the mean and standard deviation as it is, the 80 and 5, and it will calculate exactly the same way. But for using normal table, we need to sometimes we need to calculate the standard normal score. So this is the probability x less than equal to 70 is same as probability that z less than equal to minus 2, and z less than equal to minus 2 means that we need to subtract the non-shaded area. Uh, we need to calculate the probability of the shaded area, and then we will subtract 0.5 minus probability that z lying between uh, 0 to 2. So since why we are doing that, it's between 0 to 2, because minus 2 to 0, this probability is same as 0 to 2. Why is that? Because this is a z follows standard normal distribution with mean equal to 0. So it is symmetric about the 0. The probabilities of the left and right will be the similar. So if we have a similar area on the left side of the mean, and we have a same area at the right side of the mean in this case, so if we calculate that thing, so we can calculate probability z 0 to 2, and that will be same as this area, that minus 2 to 0. And if we calculate that thing, then we'll get this 2.28%. So that's how we do it. And solution above 82. So again, we calculate the z-scores the same way. 82 minus 80 by 5, that's 0.4. And then we calculate that, we want to calculate that greater than 0.4. We do that that z 0.5 minus z lying between 0 to 0.4, and then we get this, that 0.3446, or 34.46%. So that's how we calculate the proportion of students that has got a score above 82. So another exercise is that using the same probability scale, sketch the curve and find that the probability between 75 and 90, and how many got scores below 87 and above 87. So in all these cases, we again can calculate the z scores and then use the normal distribution table to calculate it, or we can use R directly like fixed mean need to be 80 and standard deviation equal to 5, or in the other case, say if we want to calculate more than 82, then we do that 1 minus p norm 82 mean equal to 80, standard deviation equal to 5. If we want to calculate in between 75 and 90, then p norm 90 mean 80, standard deviation 5 minus p norm this. So that's what we can do it. That's how we can do it in R. If we run these codes, we will get the exact probabilities in just one line of code. So it's really simple to do it in R. And so this is another problem. Molly earned a score of 940 on a national achievement test, and the test uh, mean score was 850 with standard deviation of 100. What proportion of students had a higher score more than Molly? Assume that the test scores are normally distributed. So there we can do it in the same way. This is left as an exercise, and please try this on your own, and then I'll do it. Thank you. So this is today's class.